Hello everyone and welcome to another day of Advent of Code. Unfortunately, I'm still under the weather today and my voice is completely gone. But I don't want to get any further behind, so I'm going to try to catch up today. I've whipped up a simple web app that allows me to type stuff and have it read out to you. Sorry, I don't love the computer-generated voice either, but we'll have to deal with it for a couple days until I get my voice back. Anyway, without further ado, let's jump into the next puzzle. Day 8, Treetop Treehouse. The expedition comes across a peculiar patch of tall trees all planted carefully in a grid. The elves explain that a previous expedition planted these trees as a reforestation effort. Now, they're curious if this would be a good location for a treehouse. First, determine whether there is enough tree cover here to keep a treehouse hidden. To do this, you need to count the number of trees that are visible from outside the grid when looking directly along a row or column. The elves have already launched a quadcopter to generate a map with the height of each tree, your puzzle input. For example, each tree is represented as a single digit whose value is its height, where 0 is the shortest and 9 is the tallest. A tree is visible if all of the other trees between it and an edge of the grid are shorter than it. Only consider trees in the same row or column, that is, only look up, down, left, or right from any given tree. All of the trees around the edge of the grid are visible since they are already on the edge. There are no trees to block the view. In this example, that only leaves the interior 9 trees to consider. The top left 5 is visible from the left and top. It isn't visible from the right or bottom since other trees of height 5 are in the way. The top middle 5 is visible from the top and right. The top right one is not visible from any direction. For it to be visible, there would need to only be trees of height 0 between it and an edge. The left middle 5 is visible, but only from the right. The center 3 is not visible from any direction. For it to be visible, there would need to be only trees of at most height 2 between it and an edge. The right middle 3 is visible from the right. In the bottom row, the middle 5 is visible, but the 3 and 4 are not. With 16 trees visible on the edge and another 5 visible in the interior, a total of 21 trees are visible in this arrangement. Consider your map. How many trees are visible from outside the grid? This is reminding me of the puzzle called Skyscrapers. But it seems almost like an inverse of that. If you have watched any number of these puzzles I've solved this month, you shouldn't need much explanation about what I'm doing right now to get started. I just want to make sure that the testing harness I wrote can be able to find my solution and the examples to give me the feedback I need for quick testing of my solution. For more detail, watch day 2 and 3 of 2022 where I built my testing harness out a bit. We will need to make sure that we don't double count trees. Okay, I think we are ready to start. I'll start out by parsing the input, which I believe will be the same for part 1 and part 2. The input is a grid with values. The easiest way to represent that with code would be a two-dimensional array. We could have the 2D array be of type number. Not I'm thinking maybe we make it an object with a height property. That way as we analyze we can tag trees that are for sure visible as such. Since we already have an array of lines of input, we can just turn that into our 2D array by splitting the line into characters and mapping the characters into those objects. I think we are seeing the puzzle input. Much better. Okay, that wasn't too bad. Now we can work on solving the problem. So I think we could look from each of the four sides. Then once we have marked visible trees from each direction, we can count up all trees that are visible in the grid. Okay, so as we kept the original lines array intact, that means that the first dimension of the grid will be from top to bottom. So as I increases, we are looking at a new row. So J is on the other dimension, and thus as J increases we look at the next column. So this is the order we will look at them. Now, I'm starting to think that instead of looking from all four sizes, we can just iterate through the grid once and have the tree look outward until it either sees the edge or a taller tree. So we will keep going through this investigation in all directions until we know we are seen, or run out of options. So we start with the tree's left neighbor and move left. But if at any time the tree is seen, we stop. That should never go beyond the bounds of the array since we have the x greater than 0. Boom. But actually we need to stop if the tree is definitely blocked too. No reason to keep checking. Okay, that's getting ugly, but I think it should work. We decide to keep going if we haven't proven the tree can be seen. We haven't found a tree blocking in this direction. We haven't gotten to the edge in this direction. So those three conditions will determine if we keep looking. If we get through the entire direction and haven't had anything block it, then we set is seen to true. Otherwise, reset is blocked, so we can start looking the next direction. Okay, I think that should work.
Dad, you need to see this. Okay, I'll get Mom to see it first.
Sorry about that.
Daddy. Daddy.
For the next loop, we will do similarly. But the other direction.
Other beach camera.
I'm curious if we run at this point, what will happen? This looks pretty good.
gonna go here. Make it almost as it. Almost.
Oh. I think we need to change out 4 or equals to.
We go down. It's way after this.
Okay, let's do the other 2 directions and see what happens.
I fell down. My God. With that, I think it's Hazel.
Yeah, I think that was wrong before.
It's Hazel. It's Granny. Daddy. It's not. It's not. Walk. 1, 2, 3. Wait, this count. 1. Walk. Twinkle. 8, 9. That 1 lock. Twinkle. 80. You 55 bets the daddy is on the book. You see that?
I think those are the right values to get that cell. We shall see.
Okay. You be in a build this part. You build backpack. It's break. It's break. You see that? Ah. You build it. I build it. Ah. Look. It's a great way.
Okay, that's weird. Auto formatter. But what I'm doing here is similar to what I've done before for summing things up. Only this time it's 2D, so the outer reduce calls an inner reduce and totals things up. I have to make sure that the adding is done only after determining whether the tree is a 1 or a 0. Yay! Content with the amount of tree cover available, the elves just need to know the best spot to build their treehouse. They would like to be able to see a lot of trees. To measure the viewing distance from a given tree, look up, down, left, and right from that tree. Stop if you reach an edge or at the first tree that is the same height or taller than the tree under consideration. If a tree is right on the edge, at least one of its viewing distances will be 0. The elves don't care about distant trees taller than those found by the rules above. The proposed treehouse has large eaves to keep it dry, so they wouldn't be able to see higher than the treehouse anyway. In the example above, consider the middle 5 in the second row. Looking up, its view is not blocked. It can see one tree of height 3. Looking left, its view is blocked immediately. It can see only one tree of height 5 right next to it. Looking right, its view is not blocked. It can see 2 trees. Looking down, its view is blocked eventually. It can see 2 trees, one of height 3, then the tree of height 5 that blocks its view. A tree's scenic score is found by multiplying together its viewing distance in each of the 4 directions. For this tree, this is 4, found by multiplying 1 by 1 by 2 asterisk 2. However, you can do even better. Consider the tree of height 5 in the middle of the 4th row. Looking up, its view is blocked at 2 trees by another tree with a height of 5. Looking left, its view is not blocked. It can see 2 trees. Looking down, its view is also not blocked. It can see 1 tree. Looking right, its view is blocked at 2 trees by a massive tree of height 9. This tree's scenic score is 8, 2 by 2 by 1 asterisk 2. This is the ideal spot for the treehouse. Consider each tree on your map. What is the highest scenic score possible for any tree? If a tree is right on the edge, at least one of its viewing distances will be 0. That means that the scenic score for edge trees will always be 0. So this is what I think we need to do. Similar algorithm as before, only instead of looking until we know it can be seen, we keep a total for each direction. Then we multiply that to its scenic score, with the initial value being 1 times any numbers multiplied to it. Okay, we are ready to code it up, I think. Putting this in the common parse function shouldn't mess up the part 1 solution. I think this should work. We could also put another condition in there such that if the scenic score is already 0, we just stop trying. But I don't think that making this more complicated in the condition is a good idea. Maybe I extract it out. Actually, I don't care about tree dot is seen anymore. Well, that didn't work. Oops, I coded part 2 in the part 1 function. Phew! Okay, I wonder if you need to add to trees seen even if it blocks your view. That would make sense. I think I have it. Now I just need to find the largest in the list. I can't believe I didn't think of this on part 1, but I can use JavaScript's flat function to flatten the array, or flat map. Oh darn. I guess flat map is for when you map then flatten, but here I want to flatten then map. Much better. I want to sort descending. I probably didn't need to sort there, which will iterate multiple times over the array to sort the entire collection. I could have done it in big O again time if I had instead just kept a variable of the largest value I had seen, replacing it if I see something bigger. Could have even used reduce to do that. There, now no matter how big the collection is, we will only have to scan through it once. Hooray! That's it for this one. Thanks everyone for watching, and I hope you enjoyed this puzzle. I'll likely take a quick break, then start a new live stream for the next puzzle, so stay tuned if you want to see that one live. Regardless, until next time, take care of yourself, and I'll see you later.